Greetings, everybody, once again. This is Timur, and welcome to our webinar devoted to getting started with the exabyte.io platform. Let me share my screen, and let's go ahead and start this presentation. So a few things I want to go through before we start. The goal of this webinar is to help users understand the concepts behind the exabyte.io platform. And this is the first webinar in the monthly recurring series. First Fridays of each month, we speak about getting started. And third Fridays, we talk about advanced topics. Every participant should be a registered exabyte.io user. And every participant will receive a copy of this presentation in a PDF format. And we will distribute the recording of today's session as well. If you have questions at any point in time, please use the chat functionality or the Q&A to ask those. And we will have dedicated times during today's presentation to answer the questions. This is the agenda that we can use today. First, we'll focus on the overview of the platform capabilities and the vision behind what we're building. Then we will proceed with the core parts. Things that are under the hood, the common user interface components, actions, and the accounts that the platform works with. And then we will proceed with the discussion of each of the individual entities that the platform supports today, like materials, simulation workflows, calculation jobs, and such. So without further ado, let's start with the vision and the mission behind the exabyte.io platform. And here we have to take a step back and look at the research and development landscape and how it evolved over the last 5 to 10 years. Traditionally, we were versed into experimentation, into theory, and since 1950s into computational science. And the landscape of R&D is now changing and adopting to the fourth paradigm, here the data-driven science, where we can use the results of each of these three, experimentation, theory, and computation, to be able to see the trends and data that they produce. And these trends help us understand and draw conclusions based solely on the data. And that's why this is a new paradigm, and that's why artificial intelligence in particular is the most powerful tool that is enabled by this new paradigm. However, in order for this paradigm to work, we have to have data that is well organized, right? We have to be able to utilize the tools that come from the first, second, and third generation and organize the data that they produce. So what is required to facilitate this new kind of digital tools? We believe that we have to first start with a focal point where multiple different kinds of users, multiple different kinds of data can come together. And we call this focal point a cloud. Not necessarily a public cloud, it could be a private cloud, but a place where different kinds of users and different kinds of data meet. And this could be computational scientists, experimental scientists, data scientists, IT administrators, the R&D management. All of them have access to this focal point, the cloud. And then we have to be able to ingest data coming from multiple different tools. And this could be in-house tools, commercial, open source. And all of those tools, all of the data have to be organized in a database to be able to facilitate artificial intelligence and machine learning. And to facilitate the security and avoid any kind of intellectual property leakage, we have to make sure that this picture is the platform that is deployed is secure as well. So that's in a nutshell what we do at exabyte.io. And in order to implement such a platform, we start with a set of open source components that together form the foundation of a fair R&D ecosystem. And fair here stands for findable, accessible, interoperable, and reducible. It's a well-known data science term. and we embrace it in building the platform. So we start with a set of data standards for entities that the platform operates with, such as material structures, simulation workflows, calculation jobs. And we produce a set of extractors that can take information in native formats produced by other tools, simulation packages, for example, and convert it into the standards that we operate with in the platform. And again, these are all open source tools. For users to be able to work with this data standards, we have to provide the user interface. We have to provide things like RESTful API. And that's what we call applications, where users can come in and interact with the data that we store inside the platform. Instead of going to a native format, of which there are dozens and dozens of different formats, we suggest that our users utilize the standards that we provide inside the platform. The second component and the use case that we start from is the use case for the computational scientists, where they utilize our platform and its computational tools, either in the cloud or, as you can see now, in the next step, in the next slide, through on-premises deployment. And by using the familiar tools and the extractors that I just explained, they can create data that is then stored in the exabyte platform accessible online. All of these are parts of the exabyte platform, except the users. And this picture allows us to produce data, organize it, and make it available to a larger set of users within the platform, so that we can facilitate exchange and collaboration. Besides the computational sciences, we also have experimental sciences, of course, and data sciences that need to operate within the same platform. And we have support for all these three key user types. And then, the larger organizations, especially, there are certain external elements. And of course, for people who work and experiment, they must be able to connect them and feed in the results of their laboratory equipment. And that completes the picture. The external elements come together with the exabyte platform, which is available online or on premises, and the open source components to complete the ecosystem for the digital materials R&D of the future. So if you think a little more in depth into the digital materials R&D lifecycle, we can identify at least 7 different components, where we have to design materials, structures. We need to then design modeling workflows to be able to characterize these newly created materials. We then have to take care of provisioning the high-performance computing infrastructure, control and assert the completion of these calculations, collect the data, build analytics based on this data, and find experimental validation. And as of today, the exabyte-io platform supports 6 out of the 7 steps. So let me demonstrate to you some of the functionality that it supports. Here is an example picture that represents an account in the platform. This is our team account for exabyte.io team. As you can see, we have multiple users that belong to this team, and we hold multiple different entities as part of this account. The materials that we have created, the workflows that each of the members of this team have created and shared, simulation jobs, and some additional information as well. So point number 1 in the digital R&D lifecycle is to create material structures. And here is a quick example how this can be done. We can utilize materials design functionality available through the platform to design things like interfaces, surfaces, crystal structures, and so on. Besides just the singular structures, we can create a combination of the structures, like the chemical reaction images, as shown here. We have initial and final state of the chemical reaction, and then interpolate different structures in between them. You can see here we support this functionality as well. Second step in this succession is to design a simulation workflow. And for this, we have a set of templates that are available inside what we call a workflows bank that contains unique copies of all the workflows designed in the platform and shared in the public domain. And these workflows allow us to study a set of certain properties, such as electronic band structure, phonon dispersions, and energetics of the system that we have just designed. So when we have a chemical reaction, we can characterize each of the steps in the chemical reaction according to a particular simulation technique. And we support things like density functional theory, molecular dynamics as of today. So step number 3, once we have designed the workflow and once we have a material as well, is to combine them together and execute the simulation. So in this case, I'm looking at the gallium arsenide band structure and making sure that the calculation proceeds as expected, and at the end produces a result. Okay, so these results are stored in a database and then can be extracted and associated with the structures and the workflows that we used for this calculation. For the matched elastic band, there is obviously another example. There is an example reaction profile extracted in the NEB calculation. And for people who use this on a daily basis, we support programmatic means of dealing with each of the 4 steps before, so that they can deploy Python scripts or utilize the RESTful API endpoints directly to create materials, to create simulations, to run them, observe the completion, and then extract the data out of it. So we can do things like, again, import materials, create jobs, wait for them to complete, and form a data frame based on the data that is produced inside those calculations. And this allows for high throughput calculations for really looking through thousands different formulations of a compound and doing that in a short time frame. So that's how the resulting data would look like for energy band gap calculation. Okay, data scientists, for many data scientists and for computational scientists too, Jupyter is a familiar tool. And here is how we can utilize it to do data analytics within the Exabyte platform. So we can utilize Jupyter in the combination with, so if we go on inside a job and then click on the notebook, we can have a live Jupyter session within the platform utilizing the data that has been produced by things like density functional theory previously. And by using the RESTful API credentials, we can now start interacting with this data. That's what the video demonstrates. So we can, for example, query on materials that have certain element in the formula. Okay, and this query is designed according to the data standards that I described in the very beginning. Here's the set of applications that we support right now. And this set includes things like Quantum Espresso, VASP, LAMPS, and WChem, and such, so the DFT engines and molecular dynamics engines like CP2K, LAMPS, and so on. We also have a set of analysis tools like VMG, XCrystal, Vesta that can help analyze the data that comes as a result of the application of these tools. And we support the execution of Shell and Python scripts as well. So for people who like command line interface, we provide that as a way of accessing the platform too. And here's a set of modules. Environment modules is the software that we use to enable command line interaction with all of these different software packages. And people familiar with batch scripting can utilize that to run calculations. Here's a quick example how we can do that. You can navigate to the platform, select terminal in the right-hand sidebar, and then create a job script, submit it, make sure that the calculation is running shortly, and then work with the results of this calculation. So let me summarize for you here. The first part of today's presentation is about the mission of the platform and its capabilities. And really, our mission and our vision for the platform is to be the comprehensive ecosystem for materials and chemical R&D. And our goal is to transition today's prevalent, isolated, fragmented approach to this findable, accessible, interoperable, reusable concept instead. And we built the infrastructure, the data infrastructure, the computational infrastructure, and combine different parts of it to make this possible. Now, the goal of the platform is to supercharge the scientists, to give this capability to utilize computation for the purpose of materials R&D to a larger subset of people that do material science, and to supercharge the people who already use it today. And as you can see, the platform can be accessed at multiple levels, either through the graphical user interface, through command line, through RESTful API, and such. Excuse me. Now let's speak a little about the core parts of the platform and what's under the hood. Coming back to the diagram I demonstrated to you before, we can see that many parts of many icons inside this diagram also represent the software repositories that are available on our GitHub account page. For example, standards are expressed inside the repository called SE, which stands for exabyte source of schemas and examples. And we have other components there too. So why is it important? It's important to understand the entities that the platform works with. And we on purpose have spent time to isolate these entities. In most cases of the computational material science today, information about the workflows and materials usually is bundled together, and we separate this information on purpose. That helps us support multiple different materials formulations and isolate the logic that we have inside the workflow and manage it separately too. Now, to understand how these different entities are represented, we can navigate to SE, the GitHub page of the repository, and see some of the examples. This is an open source repository, and it's reusable as Python and JavaScript projects. So users that are building web applications in JavaScript, for example, they can assert that the data that they work with in the end adheres to the standard. And here is an example of a material schema. That's how we represent a material that contains, it's a JSON object that contains a certain set of keys. And each of these keys could be another, could have a schema of its own. For example, bases have its own schema, which is explained in a separate file, included here as a reference. And here is an example of how we store FCC silicon, example material, and its basis, right? It has coordinates, it has elements of each of the coordinates, and a set of additional data associated with the structure. When we work with the platform, we can access this raw data by utilizing the expand functionality on the list of materials. And this allows us to see more of the underlying data that each of these materials entities represent in the platform. In the table, we have only a small subset, but if we expand it, you can see the entire JSON object. So every entity that user encounters inside the exabyte.io platform is defined inside the exabyte data convention, or as we call it, SE, the essence of all the work that we do. The definitions are meant as a unified format to be able to incorporate support for additional types of materials, molecular structures, nanostructures, and additional types of modeling approaches beyond what we support today. And the platform provides a user interface to work with this data, and we can also use RESTful API to extract it. We welcome contributions from the community. Here is an example pull request that some of our users opened on GitHub to implement a particular additional functionality for the materials designer. Materials designer is an example open source application that allows to modify the materials structural data, and users familiar with JavaScript can develop certain functionality, submit a pull request, and then see it available online within the platform. Now let's speak a little about the user interface and the main components of the user interface as they are shown in the platform. As you can see here, we have 5 main components, and that includes the header at the top, which contains triggers for the left-hand sidebar and the right-hand sidebar, and the left and right corners accordingly. And we have footer at the bottom, and we have the support widget in the left bottom corner. And for people who are just starting with the platform, the support widget is probably the most important component. And let me start with explaining what it does. So that's how the support menu looks once we click on that button. That's the support contact us form. So if you have a question, if something doesn't work or something is unclear and you are logged in on the platform, that's how you can communicate with our team. And we really, unless it's a very generic question, we really encourage you to include an attachment with a screenshot, at least a screenshot, maybe even a screencast to explain the problem better to us so we can quickly respond and help you. There is also, before you are logged in the platform, and if you persist the browser session, if you do not reload the window of the browser after you log in, there is also a right-hand chat tool. And although it is present there for logged in users too initially, we discourage its use when you are inside the platform. It's really there it's really meant to help people who are just researching and going through the process of the registration to communicate with our support team. Okay, now let's continue on and look at the left-hand sidebar. You can click the left top corner to trigger it. And here, as you can see, we can access the entities that belong to this account that we are currently logged in under. Things like materials, workflows, simulation jobs, and such. In the right-hand sidebar, which we can open equivalently by clicking on the right top corner, we have things like account preferences, billing and payment, and the alternative connection means like terminal and the remote desktop. There are also components that are entity specific, but we can group them by the function that they provide for the entities. For example, there is an Explorer component which lists the entities. There is a designer component which represents usually an online development environment, an IDE, for the creation and editing of one of or more entities like materials designer. And there is a viewer component which helps us view a particular entity or multiple without modifying. So here's an example entity explorer for materials. You see we have a list of materials that are available to this account and a set of properties that are associated with each of the materials. We also have at the top tools that can be applied to each of the entities in the list. And we have drop-downs for each of the entity to apply a specific action to only a single entry. At the top, we also have the search bar that can help us filter the entries in the list. Now, this is an example designer component, and I will speak about it in more details shortly. This component is an integrated development environment available online in our platform that allows us to design material structures and modify the data that we have inside our account. It's also an open source JavaScript application, so that for building web applications, working on the web, can utilize it to add materials design functionality. Here is a materials viewer page, which shows the 3D representation of a particular structure, and its crystallographic information as well as its metadata. In the viewer, we cannot adjust the crystallographic information because it would modify the structure itself, but we can change the metadata. We can add or change the name, for example. Now, the entities in the platform are owned and operated on by the accounts. And accounts could be for individual users, or it could be team or organizational accounts. Personal accounts, accounts for the individual users, have only one member by definition, and organizational accounts can have multiple members. And these members can have different types of permissions on each of the entities, such as read and edit. And account members have shared access to all the entities that are created under this account. We also have a concept of the entity collection and entity bank. So by default, each account has its own private entity collection. So materials, workflows, jobs, everything that is created under a particular account belongs to this account and is associated to it. But inside the bank collection, we store all the unique entities. For example, when we have multiple users, in each of them are initiated with Silicon FCC as a default material. This leads to duplication inside the entity collection for different users. But inside the corresponding bank collection, we only hold a single unique entry. So it helps us keep track of what happened inside the entity collection and which entities are unique. So when the accounts have private data enabled for them, which is an optional feature in our platform, no other accounts can access the corresponding entries inside the bank collection. And when this option is not enabled, other accounts can see the entries that are produced inside the bank account. So it's a premium feature. It's an additional protection, additional privacy for certain accounts. If you're really working on an open source, in an open source domain for governmental academic researchers, and most of the time, this is not a concern. And for enterprise, of course, it is. And that's why we have this feature. So bank account can be accessed, the bank collections can be accessed by using this import from bank action inside the top level tools in the Explorer. And we endorse the use of entries in the bank created by the curator's account, because this account contains a well-curated set of entries that come from the exabyte-io. We test them, we make sure that they produce results as expected. And at the same time, you can see there are entries produced by all the other users. And sometimes, especially as they are iterating through these entries, they could be unstable. So we would encourage anyone who's just starting to use bank workflows produced by the curator's account. Accounts are governed by the service levels, which means that the set of features that are available to a particular account is defined by its service level. And we have 4 different service levels, starting from free and going on to the enterprise. And they have different set of features associated with it, and they have different type of subscription fees. For example, free obviously is free, and enterprise has its own, comes at the premium price. So when you look at the set of features, we can see that the different service levels differ in the number of account members, in the support severity, how quickly we can reply to support, availability of the number of projects that are available to the users in those accounts, and a set of other additional features. So let me summarize about the core components. Data standards define the entities, the concepts that platform operates on. And we have really meant this data standards as a unified format and an open source undergoing so that we can include feedback and contributions from other people. Our platform provides a user interface to work with these components, and it can be accessed through multiple different scenarios, like through the graphical user interface, through RESTful API. And the accounts can perform actions on the entities in a shared access way. And the features that are available to these accounts are defined as according to the service level. Okay, let's see if we have any questions as of now. Don't see any, so let's continue on. We'll come back to the Q&A at the end. So how do we work with materials? Materials are one of the entities that we hold and work with in the platform. In most cases, users already have a set of structures that they want to work with, or they have ideas, at least, about the structures that they want to work with. So the first option that we will discuss here is about uploading data from disk. So we have a CIF or postcard file, and we want to import it. Then we will click on the upload tool in the top toolbar of the Materials Explorer. And we are presented with a dialog where, that shows the files to be uploaded. To select the files, we need to click on Select Items, and we can select multiple files from disk. And now they are shown inside this temporary dialog. We can click on this file to make sure that it actually has the desired content. And we can attach metadata to some of these entries. For example, if you click on the tag tool at the top after selecting one of the files, and then we can type multiple tags separated by comma. You can see that these multiple tags are associated with this entry. Now, if we select all the entries and click Upload, these files will be uploaded and converted into material entries. The check marks are shown, and the message appears. At the bottom, we know that the materials are now created, and the data that we have on the disk now is available in the exabyte platform. And the metadata have propagated accordingly. We can see the 2 times. The second option is to import materials from an online database. And today we support a materials project as a source of crystallographic data. For that, we can click the Upload button instead and search for a materials formula. So, for example, in this case, I will search from Museum oxide, and I have 2 structures that are available to me and some additional metadata. I can also, again, expand each of these entries by clicking on it, and it will show additional data that the materials project feeds through the RESTful API, so that we can see things like formation energy and additional metadata. And then I select one of the entries and click on Import, await the confirmation, and I can see this material at the top of the list. Here it is. We can visualize the structure itself. All right, so that's how we import a material from an external third-party database. A third option is to copy a material from bank. As I said, as we have more and more users working on the platform, they generate structural content, they generate simulation workflows, and from materials, we can use that as an option. So I can click on the left-hand sidebar, select bank and then materials, and search for the formula for the material that I want to import. Magnesium oxide in this case, and then select it and copy to my account. So that instead of being in the bank account, it is now available inside my account's material collection. Okay, so that's how we import material from materials bank. There is also a shortcut at the top that we can use to navigate to the bank. It's available for materials and workflows. In some cases, the simple search is not enough. And for that purpose, we have enabled advanced search capability for materials. Advanced search allows us to build a query and apply this query to filter the list of materials down below. And this query can be built using AND and OR conditions. And self-explanatory how it works. We have multiple AND and OR conditions, and they're separated at different levels. And we have a set of keys that we can utilize to filter and combine those conditions. So in this case, I'm going to use 3 conditions. I will filter the list according to the formula that contains aluminum, volume of the unit cell that is less than 80 angstrom cube. And I will also make sure that tags contain high pressure as a string. And then if I click search, I can see now there is a single result which adheres to all of these 3 conditions. And if I click reset, I come back to the full list of materials. Next point I wanted to mention here is how to access Materials Designer. So once we have imported or uploaded material structures, we sometimes want to edit this information, or we can create new materials inside our accounts through editing existing ones. And for that, we can click on the Create button inside the Materials Explorer. And it presents us with this page with the interactive development environment, which contains a header at the top with multiple menu items. It contains the list of materials available to this session in the left. It contains the crystallographic data panel in the middle, and then interactive 3D viewer on the right. So let me demonstrate quickly how we can import a material to work with them inside the Materials Designer session. To do that, we need to click Input-Output menu and then select Import in the list. And here we see materials that already are present inside our account collection. So to be able to see something here, we have to have materials inside the account already. And then we can filter materials by, for example, utilizing the tag, the string that is available inside the tags. And then we can select it, and it becomes available as part of this designer session. We can then remove the material that is created there by default. By default, we use the default material, which you can change using Materials Explorer. Default material for the account, in this case, is silicon FCC. Right, and that's how we have imported aluminum nitride in this case, and now we can see it's visualized on the right. All right, so that's how we initialize the Materials Designer session with a material. Now, workflows have many of the same concepts that are applicable to them. For example, we can also copy workflows from the workflows bank. Just like with materials, we need to navigate to the bank page by opening the left-hand sidebar, clicking bank and workflows. And then we can search for a particular property that is extracted in this workflow. In this case, it's the event structure that I'm searching for. Select the workflow that you want to import and click copy. So in this case, after going through these steps, the event structure workflow now is available as the account entity in the account collection. So to be able to design new workflows, we have to understand first the inner structure and how we store the logic inside the workflows. For that purpose, we utilize subcomponents. Like we have sub-workflows, and each sub-workflow contains further one or multiple units. Sub-workflows we identify on purpose, and isolate them on purpose to isolate different simulation engines and different models. So sub-workflow contains a single model, and it contains a single simulation engine that is employed. And we introduced this concept really for modularity to be able to use some of the commonly applied logic. Unit is the smallest logical element, and units are executed in succession inside a sub workflow. And there could be also things like splitters and if conditions that are applied. And that's why units can have different types. They could be execution types, they could be assignment type and condition type. For example, when we assign a variable inside the unit, it's an assignment, and when we have a condition, a fork, then it's a condition unit. Execution units have executables associated with them and different flavors. So for example, for pw.x, executable from the Quantum Espresso package, we have a commonly used flavor, which conducts the self-consistent field calculation. And to be able to reuse the template for this calculation, we identify pw.sf as a flavor. Now, here is the workflow designer window. It resembles that of materials designer, and we have the items list on the left. We have a header on the top and the main editor window on the right. To be able to add a workflow, for example, we can use this editor window, click on the plus button, and then click apply. And now we have two sub workflows inside this workflow. This workflow of the band structure plus density of state. If we click on the minus button, we accordingly can delete a sub workflow. Now, the sub workflow editor window contains multiple components inside itself, and there is an action bar menu, the editor tabs, and units flowchart. And if you look at the units flowchart, that's where we can access the information about the sub workflow units. And here's how it looks like when we zoom it in. We have the currently active unit box to be highlighted. And the unit type is shown at the bottom here. And we can click on one of those boxes to open a detailed view of the unit. And to understand the logic in which these different units are connected, we have to represent it as a flowchart. And this logic that is demonstrated on the right, and if we trace it, we will come up with this flowchart. So it's really a convergence and optimization loop where we have a condition applied on the result of the WSF calculation to make sure that two subsequent iterations of this loop are not different from one another for more than a threshold. If this condition applies, then we exit. So that is how it's going to look like in the platform today. And if you open one of these units, we'll see that there is an application section, there is a properties section, there is a monitor section, and there is a part that contains the input templates. And for the input templates in particular, we can see that the language of the template derives from the original language for the Quantum Espresso input in this case. However, it contains a set of variables that are coming from the template data. And the template data itself is generated based on the materials and workflow information that we retain. So we have things like the material structures. For example, there is a crystal lattice type called iBraf for the Quantum Espresso input. We inject it here when we render this template. And we can pass multiple different materials to be able to render this template for multiple different structures at the same time. In addition, we have things like key point grid and other workflow related information that also is used to populate these different template fields. Now, that's how it's going to look like when we first render this template on the web. Once the template gets to the computational cluster, you can see that some of these variables are still not resolved. And that's because we resolve them, we render the final textual file before we start the actual calculation on the compute cluster. That's because for users, it really doesn't matter where exactly this job work directory is going to be. Although it matters when we work with this file directly in the command line, for the purpose of working with it from the user interface, it should not matter. And that's why we have this two-tiered render process when we first render the file on the web, and then render it for the second time on the computational system. This also allows us to implement things like loops and adjust the context of this execution while the calculation is running. Now, once we have the material and workflow, we can proceed to create simulation jobs. And here are, some important nodes that we need to, some important conditions that we need to make sure are satisfied before we create a job. First of all, we need to make sure that we have a material created and the workflow as well. We need to make sure that we have enough account balance to perform this calculation, and you have enough disk space or disk quota. Then we can navigate to the desired project, which is the collection of jobs that we help users organize. So if you have a particular project, like a particular scientific project that you work on, or you can isolate all the jobs accordingly inside the platform. Or if that is not a concern, we can just navigate, open the left-hand sidebar and navigate to the default projects job creation panel by using this create job shortcut. That's what I'm going to do now. And I'm going to be presented with this jobs designer component. It has a header menu at the top. It has materials, workflows, and compute tab. And as expected, materials tab allows us to select materials. We can do that by clicking on the dropdown in the header, clicking on select materials, and then selecting multiple entries, one or multiple. We allow users this flexibility. We then click select items, and as you can see, 6 materials are now present inside this materials designer session. As you notice, the name of this job also now contains a formula key, which will be injected according to the formula that we work with. So this is helpful for combinatorial studies when we have multiple different formulations that we work with different chemical formulas. And we will create one job per each formulation. Second step here would be to select a workflow, and it can be done in an equivalent manner when we open the select workflow module, and we can select one of the workflows that we have under the account. We can only select a single workflow in this case, and that's because that's by design. We can have multiple materials, but only a single workflow. Step number 3 here is to set the computational parameters, and that's a topic for a separate discussion. But as you can see, what we can do here is to set the absolute time limit to make sure that we don't overspend on this job. So by default, it's 1 hour. We can modify it accordingly. We can select the computational cluster that we will run this calculation on, which can have different kinds of hardware available to the users, including things like graphical processing units, different types of networking, and such. And then we can select different queues that have different resource management policies and the number of cores and computational nodes required. After we do that, we can click on the checkmark save button in the header, and that completes the job creation process. It's important to understand that the workflows cannot be modified during the job creation, and that is by design to simplify the user interface components and assert the data consistency. Users should modify and edit the workflows first, and then select the modified workflow during the job creation. The unit input preview field can be edited directly inside the job designer, but we discourage this because it affects the data consistency. For multiple materials, we can have high throughput job creation, or we can have multi-material workflows as well. for example, matched elastic band calculation, would have multiple images associated with it, and we would classify it as a multi-material workflow. So we'll create a single job with multiple material structures attached to it. And there is a way to span jobs within the jobs and assign them certain computational parameters, but that's a topic for a separate discussion. Once we have created the jobs, we can see that there are in the list of jobs in the pre-submission status shown in bright blue. We can then select this entry, click on run, and this job will be transferred from pre-submission to submitted state. And shortly thereafter, it will transition into the active state. The pre-submission state is blue, dark blue, and the active state is orange. When the job is active, we can navigate into it and assert that the execution progresses as expected. We can see navigate into one of the units, open its output, which is posted to the application in real time, bigger than real time. You can see the currently active unit is shown in orange, and there is this blinking component icon, blinking beacon that identifies the currently active unit, and the finished unit is shown in green. When the job is finished, it transitions into the finished status shown in green, and we can navigate back to this job and see its results. So beyond the materials, workflow, and compute tabs, now we have results in files tab. In the results, we can see results arranged by each of the workflow units that contains the information about the results extracted in each unit. And in the files tab, we can see all the files produced inside this calculation. We can visualize the content of these files, we can preview them in the browser, or we can download these files to disk. All right. So that's how we work with materials, workflows, and jobs inside the Exabyte platform. That's a quick start how we can create, edit, and modify the information about these entries. So now I have some time for the Q&A. Let's see if we have any questions. No questions in the Q&A panel, no questions in chat, as I can see. Not. Okay. Well, if no questions, I'd like to thank you for your attention. And as I mentioned in the beginning, we run the webinars twice a month. So our next webinar will be devoted to advanced topics. And it will happen 2 weeks from now on the third Friday of December. In the meantime, I wish everyone to stay safe and well. And thank you